Okay, I am re-recording this. I opted to start from the beginning, even though I was on like the third slide. So I hope that pays off. I am very tired. My eyes are very tired. I've been working on my computer all day. So I hope it doesn't compromise the video lesson too much. So we are starting lesson 2 of unit 3, finally, after camping out in factoring for a super long time. And you'll see on the screen there, it says, what on earth is a number that isn't real? So we have been working with this set of numbers called the real numbers, and we know the domain of a quadratic is all real numbers. And those of you that tend to pay attention to that naturally start to ask the question, well, what is a number that isn't real? Like, what would that even be? And in this lesson, we finally get to answer that question. Now, I'm looking ahead, and I have a feeling that I'm going to spoil the activity because I am re-recording this, so I think it's going to pop up with the Desmos piece done. And it did. I'm going to yeah. So what I want you to do is use your calculator and or Desmos to find the square root of -4 and try to cover up the screen so you don't see what Desmos says. But I do want you to actually do that on your cell phone calculator, on a handheld calculator, whatever you've got, and try to do the square root of -4. Pause the video if you need to. So I did it on my cell phone, and this particular cell phone, like the cell phone that I have right now, it just, when I hit equals, it says cannot display an undefined answer is what it says. Now, you might, if you have a graphing calculator and somebody has messed with the modes on it, usually that's not the case. That's very rare. You might actually get a calculator that spits out an answer. Now, you can see from the Desmos up here, when you put in the square root of -4, it pops up as undefined. And so you might have several different answers for that. You might have a calculator that tells you it is undefined. Some calculators will say non-real answer. A lot of calculators will just simply say error. Okay. So it won't tell you what the problem is. It'll just tell you, hey, error. So the question that's important there is, why does this happen? And I want you to take a moment and think about what a square root does. When you take a square root, what is it that you are finding? So the square root symbol is that symbol. Oh, that was poorly done. It is that symbol right there. It is different from a division symbol. I'm always surprised at how many students think that that is the same as a division symbol. It is not. A division symbol looks like that. So a square root has the little hook on it, which we're going to use. We're actually going to use that space in another unit or two, okay? Because there's actually something that can go in there. This is a division symbol. So think about what you're finding when you're finding a square root. So if you were to find the square root of 9 or 16 or 25. So you have the square root of 9 is 3, the square root of 16 is 4, the square root of 25 is not that, is 5, and so forth. What you're doing is you're finding the number that when you square that number will give you whatever is under the square root. I'm going to say that again, okay? You're finding the number that when you square that number, it will give you the value under the square root. Okay, so for 5, you take the square root of 25. If you take 5 and you square it, that is 25. Okay, so that's what square roots do. Square roots undo squaring. So you could square, let me erase all that out. I need more space than I have on the screen. Okay, go away. There we go. So if you have, say, the number 7 and you square it, you would get 49. And then if you have the number 49 and you square root it, you go backwards and you get the number 7. So squaring and square rooting undo each other. They're what are called inverse operations. And you please be careful with how you say that out loud. I hear students and sometimes adults all the time They will say square rooting when they mean squaring. This is squaring, okay? Squaring means to multiply a number by itself or a variable by itself. This is square rooting, and it is undoing the squaring. So why doesn't it work with a -4? So let's say you just go plop that -4 under there, okay? Why isn't the calculator giving you a number out for that? Well, that's because you would be looking for that number right there, a number that when you square it will give you a -4. But think about that for a second. Is there a number that you could multiply by itself and get a -4? That pause is brought to you by, I actually do want you to think about it. Okay. So you could think, well, if you take a 2 and you square it, you get +4. If you try -2 and you square it, well, that's -2 times -2, and that's also going to give you a +4. And so there isn't a number that we know of that when you square it, you could get -4. And so that's why your calculator yells at you and does this. It says, listen, I don't know what you're on about, but there isn't a number that does that. There's no number that when it's squared would give you that -4. So introducing the imaginary number. Okay, so the imaginary number. So a little history, because it's fun to talk about a little history. Oh, let me give you like what the imaginary number is. It is I. I is for imaginary. And I'm just messing up the dot on the I there. It's often scripted a little bit. That's an awful I. Like the more I mess with that, the worse I made it. Hang on, like I, like so. Okay, it's a little bit scripted, so it'll often like look like a little bit like a cursive or italicized I. You might see it written like that. If somebody is typing, though, it'll just show up as a regular lowercase I, okay? That's just usually because to click in and out of italicize when you're typing, nobody's got time for that. All right, so it has its origins in ancient Greece. There's actually kind of an interesting history about where imaginary numbers came from, or where the imaginary number came from. It was originally thought to be useless, so I thought this was an interesting tidbit of history. The term imaginary number, like why it's called imaginary instead of something else, it was meant to be derogatory. It was meant to actually make fun of the concept of imaginary numbers by implying that they were fake and useless. So if the name kind of comes out like that, it's where it came from. But they aren't useless, okay? They actually are useful. Little bit of personal history. When I first learned of them in Algebra 2, they made me angry. Now, I tend to like math, but when I was in high school, I was very indifferent towards math. I didn't like it or dislike it. Math was just, it was a class that I had to take, and so I took it. And I did well in it, but I didn't care one way or the other about it. Okay. And so just like you, when I was in Algebra 2, my Algebra 2 teacher had to teach me imaginary numbers, and they made me angry because they weren't even real. It was like somebody had to go and make up some stuff. My mom didn't care. So if you don't know by now, my mom was a math teacher, and she told me that I had to learn them anyway, and she didn't care that they made me angry. And I kind of remember having the conversation in the car, like, this is the dumbest thing. Mr. Pins was my Algebra 2 teacher, and Mr. Pins is making us do this, and like these numbers aren't even real. My mom was like, suck it up, buttercup. Okay, like you got to learn them anyway. Now, what actually surprised me later on is that I applied them in several engineering classes in college. So my bachelor's degree is in electrical engineering, and they are useful, even though most people do not actually use them. So just because you don't use a particular tool doesn't mean that it's useless. Okay, there's tons and tons of tools out there that you or I don't personally use, but they are indeed very useful for the people that use them. And that's actually where imaginary numbers are. So while most of us do not use imaginary numbers on any kind of everyday basis, they are useful. They actually do model stuff in the real world. Okay, so there's one definition, but two ways of writing it. So if you recall, like the problem that we had with the square root of -4 is that there wasn't a number that when you squared it, you could get a -4. And so what ancient mathematicians did was they invented one, and we're calling it I. And I squared when you square it is equal to -1. Now you might be thinking, but that number doesn't exist. It does not exist in the real number system. So if you were to look on a number line, okay, this is called the real number line. There is no I on that number line anywhere. And that's one way you can tell whether a number is real or not. If you could find its location on the number line, it's real. But I is not on that number line anywhere. Okay, it is a totally different kind of number, and it behaves in its own way. And that is that when you square it, you actually do get a negative. Now, the other way to define it is this. You could say, hang on, you could say I is equal to the square root of -1. Now that's really the same definition. It's just taking the equation on the left and you square root both sides of it and you'll get the equation on the right. It's kind of useful to think of just, I don't know, instead of going through that process, just kind of have both forms in front of you. So what do you need to be able to do with this imaginary number, okay? What's going to be expected of you? Well, you are going to be expected to simplify square roots that have negatives. Okay, that's going to be a skill that you would have to demonstrate. And you're not really going to be able to rely on Desmos to help you with it. Now, there is a way, there is something I can show you on Desmos that's actually a pretty brilliant, like, strategy. And it's not a trick in the sense that we can't explain it. We can explain it. The problem is that most students don't value that and they just use it as a trick. But anyway, you'll have to be able to simplify square roots with negatives. You will have to add, subtract, and multiply complex numbers. We are not going to do division of complex numbers, okay? At least not at this time, but you will need to add, subtract, and multiply them. And you will need to recognize imaginary roots or imaginary zeros in polynomial graphs. We'll touch on that in this unit, and we'll get more into that in the next unit. So those are the things that you are going to be expected to do with imaginary numbers. Now, maybe someday you will use them to analyze and design circuits. Never say never. Just never say never. Okay, so just because you're not thinking about, well, I'm going to go into a career that actually uses imaginary numbers now, doesn't mean that you will not change your mind about that in the future. Okay, so problem type number 1 is that, I don't know why I titled it this is super weird. Problem type number 1 is the simplifying the square roots, okay? Now, I am assuming that you do know how to do basic simplification of square roots. If you don't, let me know. I can link you over to like a video or some resources, maybe if I have, I don't know if I have a video for simplifying square roots, but I could come up with one. Actually, I might have one. So let's take a look at the square root of -4. So this was the original problem that we did. And for this problem type, this is the definition that is usually pretty handy to have, okay? So to do this first problem, I would have the square root of -4. And what I'm going to do is recognize that the square root of -4, that -4 is equal to 4 times -1. So essentially what I'm doing there is I'm factoring the 4 and I'm factoring, or -4, and I'm factoring it into something that I know is a perfect square and the -1. I'm going to pull that -1 out. Now there's a property of square roots that says this, that if you have the square root of a product, that's the same as the product of the square roots. And now I can take the square root of 4, which I know is 2, And then I mentioned for this problem type, it's kind of nice to have that definition handy. I is equal to the square root of -1. And so the square root of -1 is I, and the answer to that problem is 2i. So if you're wondering, well, like, what was the answer again? It is 2i. All right, the second one is the square root of 50. Now, this is a little bit more challenging because 50 is not a perfect square. So when you go to factor it, you are trying to factor it with one of those perfect square factors, okay? So when I go to factor it, I'm going to factor it like this. 50 is 25 times 2. And then because it was a -50, I'm going to have that -1. So I'm going to pause for a second and just make sure that you guys see what I did there. Now you might be wondering, well, what about 5 times 10? Could you do 5 times 10? Well, it is true that 50 is equal to 5 times 10, except that I can't take the square root of 5 or the square root of 10. So it doesn't get me anywhere. However, with the 25, I know that I'll be able to take the square root. So when you choose your factors, you want to choose ones that you'll be able to take the square root of. So this would split up into the square root of 25 times the square root of 2 times the square root of -1. The square root of 25 is 5. The square root of 2 you cannot do anything with, and the square root of -1 is I. Now, one additional step. Some of you are handwriting challenged, and you probably know that you are. It's like not a surprise by the time you're in high school if you're handwriting challenged. Some of you are going to do this, okay? And depending on how handwriting challenged you are, it might get a little bit difficult to tell if the I is supposed to be under the square root or not. So the way that I have that written over here, it is not clear whether the I is supposed to be under the square root. It's not, okay? The only thing under the square root down here is the 2. So what we do a lot of times to make sure that there is no confusion is we will write the answer like this. We'll put the I on the front side of the square root because it's all multiplication, okay? It was all multiplication in between there, and you can multiply in any order that you want. And so we will just switch the order of the multiplication there and put the I out front, and then there's no confusion. Okay, so what I'm going to ask you to do, if you are doing this from home, is pause the video, and I want you to try to do these 2 problems. So take a moment, pause the video, try to do them, and then unpause the video, and we will go over them. Okay, so for this first one, what you wanted to have done was recognize that 49 is a perfect square. And when you factor it, you're going to pull out that -1, which is going to allow you to do the square root of 49 times the square root of -1. Square root of 49 is 7, and the square root of -1 is I. Now, at this point, some of you are probably starting to notice a little bit of pattern, and you're probably wondering, can I take some shortcuts? Like, does a negative under the square root just mean that I'll have an I in my answer instead of not having an I? Yes, that is exactly what it means. And yes, you may absolutely take that shortcut. So most math teachers, okay, would do the problem like this. We would go from square root of -49, we'd go straight to the 7i. Okay, we do not write all that out. We just know and understand that that is the process behind the answer there. All right, and then the next one, you do want to factor this, and here's the deal again. So you could do 6 times 3 times -1. The problem is that you can't take the square root of 6 or the square root of 3. You want to pick a number that you can take the square root of. So instead of 6 and 3, you would use 9 and 2, because 9 you can take the square root of. That will split up into the square root of 9 times the square root of 2 times the square root of -1. The square root of 9 is 3. The square root of 2 you can't do anything with, and the square root of -1 is I. And then that last step is just to avoid any confusion about the placement of the I. So you should have 3i root 2. And that meets the first requirement of what you would be expected to do with imaginary numbers. You would be expected to simplify square roots that have them. So that brings us to what is a complex number. So we introduced imaginary numbers, and now Ms. Steeler's throwing something else at you. A complex number is actually not particularly complex in the way that you might normally think of something being complex. A complex number simply has a real and an imaginary part to it. That's it. So there's two parts of it. It takes this form, A plus BI, where A is the real part and BI is the imaginary part. Okay? That's it. Might help to see some examples. So 3 plus 4i is an example of a complex number. The 3 is the real part, the 4i is the imaginary part. Now, you can also have negatives in here. So you could have 2 minus 3i. Okay, so 2 is the real part. Negative 3i is the imaginary part. And you could also have decimals and fractions and all kinds of fun stuff. So you could have 1/10 plus 2/3 I. Okay, you kind of hope you don't see something like that, but you could, right? And that's all an imaginary number is. Now, or a complex number is. It's got the real part and the imaginary part. Now, if the real part is 0, you could see somebody write it like 0 plus 2i. That would be considered what's called a pure imaginary number. And then most of our real numbers are actually 3 plus like 0i, where the imaginary part is nothing, is 0. Okay, but a complex number has both parts to it, and you put the real part first and the imaginary part second when you write it. So let's talk about adding complex numbers. This is about as simple as it gets. You can only add real parts with other real parts and imaginary parts with other imaginary parts. In other words, you can treat the I like it's a variable. It's not a variable, okay? A variable is an unknown. I is not an unknown. We know exactly what I is. I is the square root of -1. So it's definitely not a variable, but it is represented by a letter, and therefore we can treat it the same way that we would treat other things that are represented by letters, namely variables. So for this first one, typically most teachers are not going to show any work for this, nor do we require you to show work for it. But the very first time that I'm going to demonstrate something, I am going to show you how the process works. So I've got 2 minus 3i plus 5 plus 6i. So we have two complex numbers there. The first thing I'm going to do is remove the parentheses. And in this particular case, I usually will say that the parentheses are what are called cosmetic. Okay, and if you think about, well, what are cosmetics? Most of you, if I say, what are cosmetics? You'd say, well, that's like makeup. Okay, like the cosmetics counter somewhere. And so makeup, if you think about what makeup is, makeup changes how something looks, but not how it works. And so you could put on like eyeliner, mascara, and all kinds of stuff, and you can change the way your eyes look, but you don't change how they work. In an addition problem, the parentheses are cosmetic, and all they do is they serve the purpose of separating the two complex numbers from each other, but they don't actually have a mathematical, like they don't affect the mathematics of it at all. Now, remember what I said about you can combine real numbers with other real numbers and imaginary numbers with other imaginary numbers. What I did right there was I applied the commutative property of addition, which says that negative 3i plus 5 is the same as 5 plus negative 3i. In other words, you can switch the order, just make sure you bring the sign, and then you add the real parts with the other real parts, so you get 7, and then you combine the imaginary parts, negative 3i plus 6i, which is 3i. And your answer is 7 plus 3i. Most of you are going to do that without showing any work at all. Okay? That's what most of you are going to do. You're just going to do this. 2 plus 5 is 7. Negative 3i plus 6i is 3i. Boom. Done. And that's completely okay. Second problem, I am going to do the removal of the parentheses again. You might find this a little bit awkward where it's like plus and then a negative. If you'd like to change that to subtraction, you can. And then what most of us would do is we're not going to bother rewriting the order. We're going to say negative 3 plus negative 2 is negative 5. And 2i minus 5i is negative 3i. Okay. There are your two practice problems. Pause the video. Take some time to actually practice doing them. Do not just let the video run out, okay? And then we'll check the answers. All right, so for this first one, we have 1 minus 7i plus negative 4 minus 2i. And so I'll be doing 1 plus negative 4, which is negative 3, and negative 7i minus 2i, which is negative 9i. And then the next one down, 4 plus 2i plus 3 plus 10i. 4 plus 3 is 7. 2i plus 10i is 12i, okay? Moving on to the next skill. Subtracting complex numbers, which for some reason I did not put any animation on at all. I don't know. And the next slide looks a little messed up too. I did mention at the beginning of this video that I've been working hard really all day, so. Okay, so with subtracting, in subtraction, the parentheses are not actually cosmetic, okay? They actually do serve a purpose. So yes, they set the two complex numbers off from each other, but they also function, the second set over here functions as a grouping symbol, telling you that you are going to subtract everything. So in this kind of problem, when you remove the parentheses, you need to remember that the parentheses were telling you to subtract the group, meaning you are subtracting the 5 and you are also subtracting the 7i. Then it's just like an addition problem. So 2 minus 5 is negative 3. And 2i minus 7i is negative 5i. Now, if I'm moving a little bit fast for you, it might be due to a weakness in operating with signed numbers. And that was a huge part of that summer assignment, which a lot of you did not do. And some of you, I strongly suspect, just went to the end of the video and you didn't watch the videos, or you watched the videos while you were also playing video games or something, and you didn't really let it sink in. If, like, my doing the adding of the signed numbers really fast bothers you, that's probably the skill that needs to be worked on. All right, for the second one, same concept here, negative 2 plus 3i. Now be careful, be careful, be careful. Minus a negative means you are adding. Okay, subtraction just means adding of the opposite, and minus the 2i. So sometimes students will ask me, they'll say, oops, I didn't quite click the right color there. They'll say, well, does subtracting just means you flip the sign of everything in the parentheses? Yes, but that's a terrible way to think about it, okay? Subtraction means that you are adding the opposite. So that opposite part, yes. And you're subtracting the entire group. So therefore that subtraction and opposite applies to the entire group. All right, so what do we have here? We have negative 2 plus 1, which is negative 1. And then we have 3i minus 2i, which is positive 1i. And then we have be sure to distribute the negative. That is the number one mistake students make with subtraction problems. Number one is they do not distribute the negative. Every year I harp on it. Don't forget, don't forget, don't forget, don't forget. Generally speaking, those of you that do the practice and you do the homework, you're going to be fine. It's the people that don't do any of the practice that don't realize that they don't understand it, and then they start making those mistakes. Okay, so moral of that story is do the practice. So pause the video, work these out so that you can see how they're going to come out, and then unpause it, and then we'll go over them together and you can see if you're getting them right or wrong. All right, so for this first one, we have 2 minus 1i minus 4 plus 6i. So remember that subtraction gets distributed. So you have minus 4, and then with the 6i, it's minus a negative 6i, which means you're going to be adding the 6i. So check your own work. This is where those of you that do the practice, if you made the mistake, you're going to see it, and you're going to learn about it, you're going to correct it, and then the next time you probably won't do it, or you're less likely to do it. It's the folks that aren't going to do any practice that aren't going to make the mistake until they take the test, and then they will realize, oh my word, I'm making mistakes here. Negative 2 minus 4 is negative 6, and then negative 1i plus 6i is positive 5i. Other places where you might be making mistakes is in the operations on the sign numbers. So we will get like people that say minus 1i plus 6i is negative 7i and stuff. If you're making a mistake like that, it's the operations on your sign numbers. You are allowed to use a calculator. So if you know that you're prone to doing that, please take out your calculator. Don't just wing it, okay? On the last one here, we have 3 plus 2i minus 2 minus 4i. Again, make sure that that subtraction is going with everything. And then 3 minus 2 is 1. And 2i minus 4i is negative 2i. So 1 minus 2i on the subtraction. Okay, this one, I have a weird animation on the title, which is weird. So this is multiplying complex numbers. Use an area model when needed. Okay, so we are going to use an area model, and we're going to remember the other definition for the imaginary number, which is I squared is equal to negative 1. Not I squared is equal to negative 1. So I mentioned earlier in the lesson that it's kind of nice to have those two definitions handy. It's the same definition, it's nice to have the two different forms handy. So for this first one, I'm actually going to use an area model. And so I'm going to do 2 plus 3i. And then on the left, negative 1. Ooh, there's a typo there. That should be plus 4i. Oh, good grief. Okay. So typo, that should be a 4i, and then this should be a 4i. And I don't like my area model. It's too small. Okay. So negative 1 times 2 is negative 2. 2 times 4i is 8i. 3i times negative 1 is negative 3i. And then 3i times 4i is 12i squared. Okay, so just like with anything else, okay, you're going to combine your like terms. And so we're going to have 8i minus 3i. So my answer is going to be negative 2. 8i minus 3i is 5i. And here's where it gets slick. Plus 12, but remember what I squared is. I squared is negative 1. So I have negative 2 plus 5i. 12 times negative 1 is negative 12. And then what you'll notice is we can actually simplify it more. Negative 2 times plus negative 12 is negative 14 plus 5i. Okay, I'm going to go through that one more time. Just, I'm assuming that you're writing it down, okay? So I put the first factor across the top, 2 plus 3i. Put the second factor down the side, negative 1 plus 4i. Then I multiplied to find the area of each piece. Negative 2 times 1 is where the negative 2 came from. 2 times 4i is where the 8i came from. Negative 1 times 3i is where the negative 3i came from. And then 3i times 4i is 12i squared. But remember, I squared is equal to negative 1. Then we would find the area of the whole thing, which means we will add up the areas of each box. So we'll have negative 2. These most of you can do in your head. So 8i minus 3i is 5i. And then 12 times I squared, well, I squared is equal to negative 1. 12 times negative 1 is negative 12. And then we can combine the two real pieces. Negative 2 minus 12 is negative 14. Now, remember, I squared is not the same as I, okay? And I times I gives you I squared, just like x times x gives you x squared. Now, the second one looks a little bit different. Yeah, it looks a little bit different. This you could just use distribution for. And so for this one, we might just do this like 3i and just distribute it through. So 3i times negative 2 is negative 6i. And then 3i times 4i is that 12i squared again, negative 6i. But remember what I squared is? That should be 6i. Okay, I kind of ran out of space there. So negative 6i, and then a negative times a negative gives you a positive. Now, technically, that's the right answer, but we do want to write it in that a plus bi form, okay? That a plus bi form. So 12 minus 6i. And then right here, remember that, oh, I want a different color right there. Remember that I times I equals I squared, which equals negative 1. Okay, so here's your practice. Up at the top there, it is negative 2i times 2 plus I. And then the bottom one is 3 plus 2i and then 3 minus 2i. So pause the video and see what you can do with this, and then unpause it when you're ready to go over it. Okay, so we have negative 2i times 2 plus I, and that one's just some distribution. So negative 2i times 2 is negative 4i, and negative 2i times I is negative 2i squared. But remember, I squared is equal to negative 1. So this is negative 2 times negative 1. A negative times a negative gives you a positive, and then usually we will change the order of that. And I have no space on this to do the last problem. I don't have any space. Okay, I'm gonna have to clear something out somewhere. Okay, well, hopefully you've written all that down. But it's a video, so if you needed to, you could rewind it, so I won't stress out over it. All right, so on this one, we have 3 plus 2i, and then 3 minus 2i. 3 times 3 is 9. 2i times 3 is 6i. 3 times negative 2i is negative 6i. And then negative 2i times 2i is negative 4i squared. What is interesting about this is that these guys cancel out. So you have 6i minus 6i, which is 0. And that leaves us with 9 minus 4i squared. But remember what I squared is. It is negative 1. So this is just a fancy way of saying 9 plus 4, which is 13, which is a real number. And the question down at the bottom there is, where have you seen problems like the second one before? So remember, math is consistent. We don't just learn something and then throw it out. We learn something and then we hang on to it because it's probably going to come back again. All right, so that brings us to the last slide, which is, what is your homework? Your homework is available in OneNote. At the time I'm recording this, I don't actually know what it will be, but it will be in OneNote. Most of the problems will be like these ones, but a few are going to stretch your understanding a little further, and this is a good thing. I do expect there to be questions, okay? Especially towards the end there, with the multiplication, I am expecting to get questions. So you're not going to bother me or annoy me or anything if you have some things that you want to go over or you have questions. Just make sure that you are doing the problem on your own first and that you have that work, okay? Don't erase all your work, okay? And don't just put question marks and say, I need help. Okay, make sure that you're asking questions about specific parts of the problem, and you will never, ever, ever bother me with your questions. Okay, so I hope this lesson helped. Give the homework your best shot, and then let me know what you need help with.